over a different page of the review and recording. And so all 3 pages will have a separate video that you can go and check later. So with y'all, we're going to look at the 3rd page here. So I want everybody to flip to number 16 is where we're starting. And so everybody flip to 16 in their review. All right. So it says, which of the following can be used to prove segment PQ is the perpendicular bisector of segment MN? If it's hard for you to see those letters, write them a little bigger. This is P at the top. This is M. This is Q. And this is N. You can make those bigger if you need to. It says, which of the following can prove that PQ, so that's this one, is the perpendicular bisector of MN, this one. So what does a perpendicular bisector do? What does perpendicular mean? It means it makes a right angle, a 90-degree angle. So I'm going to mark that. We want this to be the perpendicular bisector. That has to be a 90-degree angle. And a bisector does what? What does bisect mean? Cut in half. So if PQ is bisecting MN, that means it's cutting MN in half. So that means that point Q is the middle. So that MQ and QN would be equal to each other, right? Y'all agree? Check the Friday folder toward the bottom there, Kinsey, on the left paper in the Friday folder. Yeah. Uh-huh. All right. So this is how I would have to mark it for it to be a perpendicular bisector. Now the choices here say any point. We're trying to see which of these would prove that that's true. Okay. So what we have to remember is the perpendicular bisector theorem. And let's read through these, and I'm going to kind of help you, guide you to see if these make sense, because a lot of them you're just going to be able to eliminate because they don't make sense. So the first one says any point plotted along MN, so that's our blue segment. So I could put a point anywhere on MN and it'll be equidistant. Equidistant means equal distance, so same distance to P and to Q. So would it make sense if I put a point here, this green point? You don't have to draw this, just watch. Would it make sense that that green point is the same distance from P as it is from Q? No, that's not true. No way. You can see that that's not true because this is a right triangle that would be created there with that green segment. And in a right triangle, the hypotenuse, that side that's across from the 90-degree angle, has to be the longest. So there's no way it could equal this one. Okay, so that's not possible. So that's not it. So then it says, okay, what about if we put a point anywhere on PQ? So PQ is the red one. So if I put a point anywhere on PQ, so let's put a point here, would it be equidistant from both M and Q? So would those two be the same? Those two dashed lines I just added? No. Again, that makes a right triangle, and across from the 90 degrees, that has to be longer than the legs. So those would not be the same distance. From that point to Q and that point to M, those cannot be the same. Okay, so that one's out. Okay, any point plotted on MN, so let's put a point here on MN, would be the same distance to N and to Q. Well, the green point to Q is here, and then that green point to N, that has to be longer, doesn't it? Because you have to go past Q. So that doesn't make sense either. Oops. Okay, so let's try this last one and see if it makes sense. This one says you put a point on PQ. Okay, so I have this point, this green point I added to PQ. would be equidistant from M and N. Now, does it make sense that those would be equal? And like just visually, even if you don't remember the theorem, those look like they would be the same. None of those others looked like they would be the same, did they? So this is it. And the reason it's true, the reason that this works, so you can go ahead and draw